Um, this is the last week with any new content. Next week we're going to have the exam revision. What we're going to be doing is we're looking at how to turn, all of the code you've written so far has been fixed to a type. So you had to know when you were writing your linked list what the type of the thing it was going to hold. So that makes for pretty inflexible code. And so what we want to look at now is how to actually change our code so that it can hold or it can refer to any type. There are some functions we've used already which refer to any type. For example, memset. Does memset care what the kind of pointer is that you pass in? Correct, because bang on, Ross. Because it accepts as an argument a void pointer. Now, a void pointer can be assigned to. You can assign any other pointer to a void pointer without casting. The exception, I think, might be const, because const is special. It's meant to be read-only, and if you assign it to something which is not read-only, the compiler is probably going to complain about that. But otherwise, yeah, a void pointer can point to any other kind of pointer. So it's just a handle to stuff. Okay. I've covered all that. So one of the issues is that as we start to use void pointers, we now have to manage the type of the thing because the compiler doesn't know anymore. So that makes the programming harder. So you probably knew I was going to say that in a sense. It's always like that. So the issue of type safety is not something the compiler itself is managing anymore. You as a programmer need to manage the memory to make sure you're doing something valid with it. And so as you can imagine, there's more ways that things can go wrong. So yeah, like we said, we've got the void pointer. We can use size of and function pointers together to write code which is generic. By the way, you can also do it with macros, yeah? If I write a macro like this, here we go, right? Does it matter what the type that's passed in to max is? What matters? Or what's the limitation? What will actually cause a compiler error here? Yeah, but what about the parameter list? But why? Why would that cause a problem? You're right, but the why is more important. Correct. It's not a valid operation given the two operands. So this will work with anything for which greater than or equal to is defined between the types. In fact, we can mix types. We can have a double and an int, and that's fine. Although doubles with comparisons are a bit dodgy because of floating point error. But yeah. That's more of a C++ thing than a C thing. Well, yeah, you could actually implement this here. You could have a version have to define max comp of x comma y as x comma y comma comp, say, as comp x comma y is less than 0. No semicolon, but yeah. And you see that the third parameter passed in is a function. Has to be a function. So then you still got that type safety there. Alrighty. So yeah, generic program is harder to do. You need to be much more disciplined as a programmer. You need to ensure that you never cast something to a type that's invalid and try to access that data. Might do bad things. You can even treat a char array as generic through using memcopy to copy stuff into the char array. But it's typical to use void pointers because they have no type. So what information do I get from the type then? Yeah. Size is the most important thing, but there's one other thing as well, which we just saw. What you can do with it. Right, yeah. Valid operations, yeah. So we know the size and valid operations for var1, var2, var3, but it's probably more obvious why size is important with an array. And why's that? Not so much bounds. Bounds is defined by the number in the brackets. But what does the type tell us about the array? Or the layout of the array? Yes. So we know the memory layout because of contiguous allocation. We know that each element is in fact size of type. Well, that might be rounded up for because of alignment limitations. So for example, an int typically has to start on the 4-byte boundary. And in fact, most entities in memory have to start on an even byte, and so it might be rounded up. Yeah, but you can set that with packing, but that's beyond this course. Yeah. So, yeah, void pointers are a generic pointer, which means we can do dangerous and weird crap. So let me just show you an example of dangerous and weird crap. That's a technical term. Awesome. Okay. Right. Yep. Well, segmentation fault is in fact the Windows equivalent of that is a blue screen of death. Yeah? So if you get a memory protection fault on a Windows machine, that's the same as a segmentation fault on a Unix machine. So, yeah. Rightio. So I've got this function print num, right? Which accepts a void pointer. And then I print it out, I cast it to a double pointer and dereference, and then print that out. Do you think this is legal? Do you think it'll let me do it? Yep, it'll let me do anything. So then I set the entire structure to 0. And then I assign the value 150.5, and it will print out correctly here. But now, back in main, I actually print out the integer value. But the integer value has been changed by what happened in here. So it actually corrupts the data. So let's just watch that. So okay. So let's think about what's happening here. I is 50, right? So basically by the cast to double means treating that memory space as if it's double using the IEEE floating point format. And that is interpreted as a really small number. That's 2.47 times 10 to the negative 322. Right? Then I assign the floating point number and I check and it works. But then back in main, when it's an int, I print out the value and it's now 0. Now, there's a few dangerous things going on here. One of them is potentially corrupting the stack. Because a double is twice the size of an int. So, yeah, weird shit. Weird, crazy stuff. And in fact, some of my early experiments with generics some of my early experiments with generics actually embarrassingly involved corruption of the data. And it was I had to go and chase down where the corruption occurred. Where was it that the data was being misinterpreted and it was actually a different type to what I'd thought it was. Great fun. Okay, we can also write a function, a for each function. There is no for each in C, but we can create our own. And why not? So let's have a look at that. For each int.c. So I have this function fill array, which, well, funny enough, just fills the array with random numbers. Okay. Then I have another function called print array. So let's have a look at that. Well, this uses simply it's just iterating over as ints. And so if we have a look up above here, for each. So let's have a look at for each. So you see here we have a array of numbers. We have some value that we're going to combine with each number. And how are we going to combine it? That's defined by the function pointer. Right? So we go back up. So in the first case, add. So basically it's just adding the two numbers together and so on. Okay. So here we're going to do something a little bit different. In my print array here, okay, here we don't know what the type is, but we know the size, right? So basically, this is important. Okay, we start off, we grab the memory address of the start of the array. And then we iterate over the number of elements, because that count there is the number of elements. But here's the fun bit. In fact, what's going on there? Current equals char star current plus size. Can anyone suggest why I've cast this to char? Or to a char pointer? No. How big's the char? Correct. Now, what do we know about pointer arithmetic? If I've got a stuff pointer, right, and I add 1 to that stuff pointer, yeah, it jumps along by size of stuff. So implicit here, there is a multiplication by 1. Now, if there was no cast, you get a compiler warning, because we don't know how big the stuff being pointed to is. And all pointer arithmetic has an inferred multiplication by size of element. And size of type. Does that make sense? So this here is completely type agnostic. I have a for loop which addition. Multiplication by pointers makes no sense. It's illegal because of that. You can only do addition, subtraction and comparison. Yep. So then, the actual processing is handled by my print function. So that's done generically. And if I go back up the top and see what was print func, oh, there we go, it's an int. So print int. See once again we have a const void pointer to the data, and see I have a const int pointer and assign the data to it. Right? So now it's in a type which has a size. And so therefore all the ordinary stuff I can do. So printf%d, and the data in here is interpreted as an int. And I have the same kind of thing with a double. Okay? And you see, this is a nice way for me to be able to do various operations on the data. And it's in my client code, it's nice and high level, and the actual dealing with the generic data is handled in my functions. So for example, in the function print double, it handles the actual type information, and that's how it's done. This stuff's pretty important. You can't really describe yourself as a C programmer if you don't know this stuff. Yeah, but it is conceptually a bit of a jump. I understand that. Well, it's different in C++. Because C++ introduced templating. And so what happens is you write a generic function. Well, typically most modern languages have borrowed the concept of templating, in the sense that we simply create various copies of the class for whichever types we need. And that's where you get this kind of stuff, like in, say, Java or C++, something like a vector of int. What it means is we make a copy of the vector class where int is the type. C# uses same kind of idea. Not sure about languages which are type agnostic. You know, like for example, say Python, where you can assign anything into a list. It seems reasonable that perhaps under the hood they're void pointers, but I don't know the implementation. But the fact that you're getting to this point of asking these kinds of questions is good. That's the point of the exercise in some ways. Is to go, okay, this is a low level kind of stuff. So what's actually happening in these high level languages, and what's the impact that has on things like performance and so on? That's good things to be thinking about beyond this course. That will make you a better programmer. Yeah. So the kinds of I kind of jumped ahead a little bit there, but we have to use void star, and we need to bring size in as a parameter in order to write these generic functions. And because of that, we cast the char star. Mind you, I've actually written code where basically I've had a struct where basically the whole thing's a char array, and I just copy things in manually using memcopy and things like that, so I can actually write it out to disk in a single write. So char could actually be used. In some ways it makes a bit more sense, but yeah. And of course we can't dereference a void pointer. It's just a pointer to a chunk of memory. Yeah. So we need to cast to a child pointer. So you probably should think about that for each.c as a bit of a model for how we can do generic programming in C. So we have void pointers, we have size, and we have function pointers which decide which function will be called according to what the type is. And because we're using pointers all over the shop, in order to safeguard against modification, you probably should use const pointers wherever you can. Although const is not used quite so much in C as it is, say, in C++, where they just went absolutely crazy with it. Anyway. Okay, so something else we can do is we can make a generic list. So I think this is a good exercise as and it's essentially what we'll be doing tomorrow evening is taking a list and making it generic. That's what the tutorial exercise is about. So we'll spend a bit of time now having a look at such a list. So when we think about it, we have this node structure for our list where we have a pointer to the first node in our list structure, and then we have pointers going along linking together the whole list. Yeah. Now, here's our problem. In our node, we have a pointer to next, but we also have this person star data. So how do we make this list generic, you reckon? Yeah, so we actually make this a void pointer. Yeah. Instead of making... Yep, well, we'll actually use functions to actually do all the manipulation of the data. Really, this is just a placeholder. It holds the data and nothing else. Now, technically what that means is that you could have a list of varied types, but what's the problem? So we'll have an int and an int pointer, a char pointer, a double pointer, a person pointer, all in the one list. Yeah. Well, it's not so, it's the interpretation of the data. So you could do that, but then you've got to actually include other overheads. For example, you might actually have another field which indicates the type of that data. and then in fact have an array of function pointers where the you index into that array for the right function to process this data. So it gets a lot more complicated, and that's in fact the kinds of stuff people are doing when they are doing things like language design, when they're deciding what the operations are in a language. And if there's something like a variant type that can hold anything, then you've got to have some way of being able to figure out what that thing is. You need something, whether it's some kind of inference process. And so we don't have that in standard C. So what we would have to do instead is have another field which actually indicated the type of this element. So, we make the data a void pointer. And so we're going to need some helper functions as well. And in this case, we're assuming that each pointer points to the same kind of data. So this is a list of one data type, but it could be any data type. It's just one. So let's have probably what I'll do is actually have a look at the source code at this point, because it's getting very abstract without the source code. Okay. So having a look at this. So noticing in our node that we have the data and a pointer to next. But we now need to know things like, how do we compare these people? Like, how do we compare two of these elements? Well, one way to do it is in fact to provide a function pointer. So here I've got a function pointer to a comparison function, which takes in two void pointers. I've also provided why do you think I've done this? I've provided a function pointer that says how to free the data. Well, not just the size. Size, in this case, is stuff which is actually kept track of by the operating system. But there's something more important than size this time. Think about your line node in your assignment. If you free the line node, is the line freed? Now you've got line nodes where you've got a line in each one. Correct. So likewise, the structure being freed here might have pointers of its own. And so we allow another function to be provided by the user, because the user of the writer of the client code knows more about the structure than I do as the writer of the library. Think about here, I'm writing a linked list library, for other people to use, whereas all the information about the data itself is someone who's actually using my library. Does that make sense? Okay. So what's going on here? This is the new list in it. What are these other fellas doing here? Yep. Correct. So basically now in list init, I need to assign these function pointers. So let's have a look at that. Okay. So here we've got all the stuff that we've done before. Set the head to null, size to 0. But then we can assign these function pointers to the list struct. Okay. So think for a moment about your list add implementation. If we're going to make it generic and we have this kind of a data structure, what changes need to be made to the list add function? You've all coded up your own list add function by now, hopefully, for assignment 2. So think about what changes would need to be made to accommodate for the fact we now are using a void pointer. Well, that's less important this time. Size is actually less important because we have a pointer, like each node has a pointer to the data, and that's been allocated using malloc or whatever, and it's just passed in there and we assign it. We don't care what its type is. Just a memory chunk we've been given to assign to the list. Ah, yes. Good. So, if we look then at our code here. So all this is pretty standard stuff. You've seen it before. We're mallocing the node, setting its next to null, setting the data, iterating over the list. So if the head is null, it's an empty list. So we just point the head to the new node. And so here, instead of calling person comp, we call list comp. And so nothing else is different. That's simple, hey? Mind you, it's simple because I've been leading you to here all semester, right? I've actually, been getting you to use comparison functions and all of that kind of stuff. And if you've been using all of that, it's only a few steps to actually adapt to this kind of code. Does anyone have any questions? Okay. I know you probably your head's going woo, 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 but the concepts do really build on the stuff we've actually been doing, and having a solid understanding of this stuff. Well, you then can use other people's libraries for one, because their libraries will use generic types or use generic code. And in fact, a lot of the C functions you've already learnt, in fact, use generic programming. Memset, memcopy, the I/O functions for binary I/O, fread and fwrite, they are generic functions. So it's right across the language. Okay. So now what do you think the changes will be made to list delete? Well, in this case, all we're going to do, let's have a look at list print. So in list print, we provided a print function which accepts a const void pointer, and it knows the type. Right? So I just call print on the data and then move on to the next node. That was easy. So you see here we're actually calling that function pointer, the print function pointer. Okay, so now we've got our list free, and so it's the same as, in fact, there's the main change here is on this line. What am I doing here? Yep, to free the data. Yep. And that's it. So, okay, I don't have a delete function here. A similar kind of idea. You'd iterate over until, although with deletion, you might in fact have a separate del comp, because you might actually allow the passing in of a key as part of your deletion. So, but essentially what we're going to be doing tomorrow is actually going through the process of building this, so that you'll have seen the code again. I think this is also really useful if you're still, if there's any bits about linked lists themselves which you're still struggling with, good exam revision. So that's what we're going to do tomorrow. But before we go, let's actually have a look at the main function. So you see, one thing I did though, I've actually moved the person struct out of the list, because the list has no business knowing about what kind of data, and I've moved it into main, or I've moved it into somewhere I could have actually had a person module. And I have these functions which have been defined, or at this point declared. They're defined later. And I create some persons using the create person function. So let's have a look at that. You can see how well structured C code. It's almost object oriented. If you want it, if you want to go down that path, which I tend to prefer, it's my preferred style. And so, yeah. Anyway, so then I've got my person function. We have two void pointers for the first and second. And then you see I assign them to the right kind of pointer. And then do the comparison, just like I did before. So that hasn't changed. This is the function which was passed into print, into list print, to actually print out each element. Okay. And in our case, well, there's no complex data in person, so in fact the free is just free the person. So let's go back up to main. So I actually, let's double check something. Okay, there is a bug in this program. Can anyone see it? It's actually in main. Well, it's a poor practice anyway. What should I be doing after allocating memory? No. Check it succeeds, correct. In fact, the correct place to do this is basically if not Fred, This, by the way, was another misstep that people made in the debugging, is they changed not Fred, say, to, and I thought they fixed the bug. So that's clearly not a bug fix, because when we have not like this, we're interpreting the thing after it as a boolean. And so if Fred is null, not Fred will be true. Let's just do that. And that's annoying. Okay, so then we initialize our list, passing in the pointers to the functions that are going to be used. And I add the people to the list, and they will be not sorted, but sorted according to person group. And here we call list print. Notice that we need to pass in the function to print a person. That's all. Okay. Okay, make clean. Yeah, and now if we run it, they're inserted in order according to what? Last name, then first name. So that's why the Flintstones come before the Rubbles, and Fred comes before Wilma, and Barney before Betty. Okay,